So we're talking about Dijkstra's algorithm, and last time we had sort of this naive version of Dijkstra's algorithm that we figured out runs in, VE time, which is okay but not great. And so the question is, can we do better than that? And if you recall, the key step, right, is that at each time through the loop, we're picking an edge. Like we're imagining this metaphor of the water expanding out through the graph, right? And we're like, where's the place the water's going to reach next? And the way we did that was by picking some edge where we definitely already processed this vertex, but not the other one on the other end. And we say, okay, what's the distance to that vertex that we already know, plus that edge, and we want to pick that as small as possible. But we were doing that by looking at every edge every time, which is pretty terrible. And so the question is, can we do that faster? Can we have a quick way to find what that next vertex is that the water's going to reach? Okay, so here's the basic idea, or the beginning of the basic idea. So we're going to, I'll write some things here and then I'll draw a little picture. So we're going to expand our distance map. So remember before, the distance map, right, for each vertex that the water had definitely reached. So each vertex where we know for sure what the shortest distance to that vertex is, the distance map has that distance. But for everything else, it's nothing's in the distance map. And so we're going to actually expand it a little bit to keep track of the shortest known distance to each vertex. Okay, so there might be some vertices that the water hasn't reached yet. We don't know for sure what the shortest distance is, but we can say, well, so far I know there's a way to get there, at time 20, and that's the best thing I've seen. Maybe later we'll find a shorter way, but we'll say, well, for now, 20 is the best that I've seen. For some vertices that we've finished processing, like it is exactly the correct shortest distance. But then there will be other vertices sort of on the edges that we haven't processed yet that we're like, well, I know I can get there at this time. I don't know if that's the best yet. We'll also update the parent map. Parent map. Hi. I'll just say, in parallel, or well, to track. I'll just say the best known parent. So that is, right, it'll correspond to the distance map. So, if I say, well, for this vertex, I know you can get there at time 20, and that's the best I know so far. And in order to do that, you should go from this parent, right? But it might change later if we find a better way to get there. Okay, and if we do this, the idea is, right, at each step, pick the vertex, or pick the unvisited vertex with the smallest distance map value. Right, because whichever one has the smallest value, it's like, well, these are all the best distances we know. For this vertex, this distance value is the smallest of anything, which means there's no way that we could later discover a better way to get there. Because all the other vertices, the best way we know how to get there is even longer. And so there's no way that we could come up with a shorter way to get there by visiting other vertices, because it would end up with an even longer path. So in order to do this, right, we're going to need some kind of data structure. And so let's talk about what operations we need, and then I'm going to actually send you up in some groups for a little bit to talk about what some potential data structures are that we could use and how they would possibly support these operations that we need. So, so we need a data structure that, so we need it to store vertices with like key values. Right, so it's going to have a bunch of vertices in it, which are like these vertices that we haven't visited yet, but we know of a way to get there. And each one will have like a key value, which is the best known, the shortest known distance to it so far. Okay, we need to be able to remove the vertex with the smallest key value. Okay, so I want to be able to look at that data structure and say, give me the vertex that has the smallest dv value. And then we also need to, I'll draw a picture to say why in a minute. We need to be able to change the key values because, right, a vertex might be in there and we might say, oh, you know what, I actually just discovered a faster way to get there than I knew of before. We need to be able to update it. So we need to be able to update key value for a vertex. Okay, and here's why. So let me draw a little picture actually, which I think may be helpful in multiple ways. So we'll call this U, we'll call this V, and then I'm going to have like the other vertices here. So we're in this scenario, right, where okay, here's the water expanding out in the graph. So U is visited, right? So we know for sure what the shortest path is from our start to U. So I'll put our start particularly here. Right, so there's some path goes to U, so d of U is exactly the shortest distance to U. And then we discover that V is the next vertex we're going to reach. So, so the water is kind of like expanding out to here. But now here's the thing, right? So maybe, here's x, and maybe, d of x. Let's put some concrete numbers on here. So let's say d of u is, 10. Okay? And then this edge has length 5, and this edge has length 2, 3, 9, I don't know. And let's say that, d of x was equal to, I don't know, 50. Because maybe from the start vertex there was an edge of length 50 that went to x. And so we said, well, I know it's possible to get there at time 50. Okay, so, but as soon as we pick v as our next vertex, we're going to need to say, well, let's see, does that change what we know about these other vertices? So we're going to look at all the vertices next to v and say, well, x, I can now get to v in time 15, right? So d of v is 15, right? 10 plus 5. And then I say, well, plus 2 is 17. That's actually a better value than what I had. So I need to change this value. I need to update this, right, and say that's now 17. And then, x was already in this data structure, so we're going to need to change what its key value was, right? Because maybe it'll turn out that 17 is the next smallest thing, so the next loop, maybe I'm going to pick x. Right, and then similarly, we would look at this vertex and this vertex and see whether, we found a better way to get there than we knew of before. All right. Any questions at this point? I should be looking at the chat here.
Dr. Yurgi, at any point are we storing the the edges, like the actual, like from, I think it's V to X, are we storing that anywhere? Or are we just looking at the distances?
I mean, we'll have a, we'll have a, like a dictionary or something storing the structure of the graph and what the edges are, what the weights are. But
But it doesn't have to be
that's kind of given
in
to
the
us.
data structure.
That's kind of given to us initially. Yeah, we're not storing that separately in this data structure. All it needs to store is like, okay, X is in there and it has the number 50, or maybe we change it to 17 or whatever. Yeah. Other questions? All right. So I want you to get in your groups. I'll give you about, I don't know, 5 minutes, so not long, but I just want you to brainstorm, what data structures, what ways can you think of to do this? So like, um, to store a bunch of vertices with these values, to be able to get out the vertex with the smallest value, and to be able to change the value for a given vertex. Um, I don't care if you think of something really stupid, if you think of something really sophisticated. I want like a variety of methods, and then think about how long these take, right? So if you have n things in there, in terms of big theta, how long does it take to remove the smallest thing? How long does it take to update something? Come up with as many things as you can, and we'll come back in 5 minutes and kind of make a table of what data structures we might use for this. So I have made a little blank chart up here. We can write down some ideas. So we'll just go through the groups and share if you had any ideas, and we can all kind of figure out together how these would work and how fast these operations would be. So group A, I guess I didn't assign like a reporter for today, but if someone wants to share one idea that your group had. Group A, that's Savvy, Ashlyn, and Spencer. You all here?
One of our ideas was a hash map.
Okay, cool. So a hash map. What would be the what would be the like values, and what would be the keys, and what would be the values?
I do not remember what we had discussed.
Okay. Okay. So, but yeah, we could make this work. So, like, I think if we had the vertices as the keys, we would hash the vertices, and then we would store along with each vertex the value we would store would be that distance value, d of v. So I'll just say like a dictionary, a hash map. And how long would it take to remove the smallest one in that case? Did y'all talk about that?
No, but in the worst case, wouldn't it take O of n? We'd have to look at all the...
Yeah, exactly. You would, right? Because like a hash map, it's not in any particular order. Like the only way to find the smallest value would be you literally just look through all of them, you look at their values and see which one is smallest, right? Okay, so removing the smallest would be O of n, or I'll say theta n. And how about updating the value for a particular vertex?
I think that would be constant.
Yeah. Yeah, exactly. I agree. Right, that's the nice thing about a hash map. If you know the vertex you want, you know the key, you just boop, you look it up constant time. So, okay, well that's good. All right. Group L. Did y'all have another idea that was different than this one?
had thought maybe that we might put the values in a min heap. We could use a dictionary to store our current distance, and we could put it into a min heap. That way the shortest one would always be on top.
Okay. Yeah, so like a binary heap, right, with the smallest one on the top. So binary min heap. Okay. So removing that, how long would it take to remove the smallest then? Like finding the smallest is constant time as it's on the top, but how long does it take to remove it? Don't remember that.
I looked up insert. Insert was log in, I think, but removing. I'm trying to think. Remove. You can just move one of the next ones up. I have to Google it again real quick. I don't remember.
Yeah. So that's right. So it's log in too, because you can take the thing off the top. You can't just move one of the ones under it up, but then you've got to move something up to replace that one, and you kind of keep going until everything is nice again. And so, but it's going to take a long time. Yeah, so this is, we're digging way back to data structures, right? How about updating a key in a heap? And yeah, and like anyone can answer this actually. It doesn't just have to be the group that came up with the idea. But anyone remember how long does it take to if you want to update something in a heap? And honestly, this isn't something you necessarily talk about in data structures, but it can be done.
We were thinking that we would just, you basically pop it off. It's a dictionary, so you update it's constant, and then you put it back in.
Yeah, that's one way you can do it. So it's actually tricky to do that because if you want to remove something from a min heap, you have to find it first. Right? If it's not the minimum thing, if it's the minimum, it's easy to find it. It's at the root. But if it's not the minimum, it could be anywhere. And so finding it to remove it actually it takes O of n time. There's ways around that. You can store a dictionary on the side of your min heap so that you can kind of know where it is. It's tricky to do that, but you can do it. If you kind of already have a pointer to the structure, you can just update the key and then kind of just move it up or down the heap till it's in the right spot. Anyway, so it's possible to do this in login time. I will just say, I'm not going to talk about this too much. I will say that neither Java nor Python in their standard libraries have an update key operation for the standard implementation of heaps. There's different ways around it. I don't want to talk about it right now, but if anyone's interested, I'm happy to talk about it. But if you ever practically wanted to actually implement Dijkstra's algorithm, which I'm not going to make you do, you'd have to get around that somehow. But so group G, did you all have any different ideas?
No, we had pretty much just talked about a dictionary too.
Okay, cool. Group O, did y'all have any other ideas?
Well, we actually talked about both, so.
Okay, about these two things. Yeah, cool. So here's another thing we could do, and we could think about how long this would take. What if we kept just like a list or an array, but we kept it sorted by the distance. We kept it sorted by the key values, or by the keys. So we just made sure that we have a bunch of vertices and their associated distances, and it's just sorted from smallest distance to biggest, right? Or actually, let's keep it sorted from biggest to smallest, so the smallest one is on the end. So in that case, how long would it take to remove the vertex with the smallest distance?
Constant time?
Yeah. We can remove something from the end of a list constant time, right? So I'll say a sorted list. Removing the smallest is constant time. And how long would it take to if I wanted to change the distance value associated to a given vertex, how long would that take? Was that Daniel? Did you say something?
N?
N? Why would it take N?
Because we have to go through the list.
Yeah, that's right. I mean, yeah, basically. We have to go through the whole thing to find it. And then even if we can find it quickly, once we change the value, we've got to put it in the right place, which means we've just got to like shift everything over to make space for it and stick it in the right place. This will be theta of N. It's just interesting because it's kind of backwards from the dictionary thing, right? The dictionary thing is N for removing and constant time to update, and the sorted list is the opposite, right? And then the binary heap is sort of in the middle. I will mention there's something called the Fibonacci heap. Which is cool because we're not going to talk about it. If you want to go read about it, you can. It turns out that the Fibonacci heap allows you to remove the smallest thing in log n time and update any key in constant time. However, it's much more complicated to implement than a binary heap. So I'm just mentioning that it exists. So theoretically, it's kind of the fastest way to do this. But all right. So let's now. I'm going to erase this. I'm going to write down some pseudocode now. And then we can analyze it because it's going to make use of this, whatever data structure we choose, and then we can think about which choice of data structure would give us different, running times for the algorithm. So this is the non-stupid version of Dijkstra, right? So we wrote kind of a basic dumb version the other day, but here is a more refined version. So so it starts the same way, right? We mark S visited, and we set the distance to S. The distance from S to itself is 0, and then everything else is infinity. I guess I have not actually said this word yet, so I will say it now. This data structure that we're talking about, we talk about different ways to implement it. Generically, we could say what we're trying to implement is a priority queue. So maybe you remember that word from data structures. Right, a priority queue is this structure where you have, each thing in there has some kind of key associated to it, and you can always pull out, the thing with the smallest or biggest, whichever you choose, priority. So kind of like a queue, but you get things out in order of priority instead of just in the order you put them in. So we're going to create an empty priority queue. No, it's not going to be empty because it's going to have all the nodes in it. So create a priority queue containing all the vertices using DV as the key, or as the priority. Okay, and notice, right, that it works because the very first time through the loop, when we go to pull something out of the priority queue, we're going to get S, because it has priority 0 and everything else is infinity, so it's going to be the smallest. So that will work out. So while, I guess we'll call it Q. While Q is not empty, okay, we are going to remove the smallest thing. We'll say Q dot remove min. Right, so this is the very next vertex that the water is going to reach, because it's got the smallest d value. And the only things in the queue are going to be those vertices that we haven't actually finished processing yet. Right, so the ones that we don't know for sure yet what their minimum value is, but or what their minimum distance is. But this one with the smallest, we actually do know for sure. So we're going to mark it visited. Okay, and now, right, we have to do the part that was this picture that was right here that I erased, where we have to look at all the neighbors of U, because maybe now we can find there's actually a better way to get to those neighbors than we knew of before. Maybe if we go through U to go to them, that would give us a better path. So for each edge UV out of U, okay, so I'm going to put an if here. Anyone want to guess what condition I want in my if? So, like, in what case do I actually need to do something to update something about the vertex B? Or just if you know part of it, because there's going to be a few different things here. Any thoughts?
We want to make sure we haven't visited it yet.
Yeah, good, exactly. So for sure we can say if B is not visited, right, and there's something else. So,
Dr. Yorgi,
yeah.
are you talking about that V as the next vertices after we've looked at U from the DV from before?
I'm gonna redraw this picture. So here's our S. Here's our U. Right. So the water has kind of just reached U, and now we're looking at. So this is V. Right. So this is our U that we picked, and we're like, okay, the water just reached there, and now we're going to look at all its neighbors, because this is the scenario where maybe the shortest distance we knew of to V was 50, but now that we are here at U, we might discover that actually there's a shorter way to get to V if we go through U. That's what we're trying to do right now. So I want to figure out, do we need to update DV or not? That's what this if is trying to do. Does that answer your question, David?
And DV is really far away because we said it at positive infinity.
Well, yeah, so initially it was infinity, but maybe at this point it's 50 because maybe there was some other way to get there that took 50, and that was the best we knew of. But maybe we're going to discover an even better way right now.
But how did we know that?
Well, so maybe imagine that, like, imagine there's an edge here from S to V that had length 50.
Oh, gotcha.
Right? So when we processed S, we said, oh, well, okay, it looks like I can get to V at time 50, so that's the best I know of yet. That's better than infinity. And so we recorded that. But that wasn't the vertex with the smallest D value, so we didn't pick it, right? It was just kind of hanging out there, and we did some other things. Maybe we get to U, it had D of U was like 20. But now that we're here, right, we might say, oh, actually, since I can get here in 20, and this is like, length, 6 or something, so we'll say D of U is 20. Right, I'm going to say, oh, look, it looks like I can get to V in 26 now. That's better than 50, so I want to update that and turn it into 26.
Do we just do if du plus v is less than dv?
Right. So if du plus, plus the weight of this edge.
Yeah.
Is if that's less than dv. Exactly. That's what we need to say. So if du, so plus the weight of the edge uv is less than dv, Then we need to set dv. So dv is going to be equal to, or we set it to du plus the weight of the edge uv, because that's the new best distance that we know of. That is a v. I guess I forgot to initialize the parent map up here, but I mean basically we also want to keep track of the fact that I'm going to say u is the new parent of v. It's kind of like, v says, well, I know that we can get here in 50, and like the way we got there was, initially it's going to say the parent was s. But then when we do this, we're going to say, oh, forget s. No, the best parent is u. And is there anything else we have to do? There's actually one more very important thing we have to do in this if. Can anyone think what it is?
Mark it as visited?
Oh yes, there's two more important things we have to do in this if. I guess no. No, sorry, no, we don't want to do that. Because visited means that we know for sure what the shortest distance to it is. Right, so we marked u visited here. Right, v we don't know yet. Right, this is just like the best we've seen so far, but we may end up updating that again later with an even better distance. So yeah, good thinking, but actually we don't want to do that. Something else we need to do.
Do we add it to the queue?
Yeah, so it has to do with the queue. So it's already in the queue, right? But well, if you look at our table, right, we've done the remove min operation. We've never used that update key operation, but that's what we need to do because like d of v just changed, and d of v is the key that's used for that vertex in the queue. So we need to make sure that we kind of tell the queue about it. Say, hey, by the way, the key for v just changed. You might need to like shuffle things around to make sure that things are in the right place so we can get the smallest thing later. Because maybe v has now just become the smallest thing. So I'm running out of space here, but I think I can say, q dot update key. I'll say update the key of v to the new value of dv. Hopefully y'all can see that. Questions? All right, so let's analyze how long this takes. Because we're trying to make something faster than theta of VE. So I don't know, I'll use green again. So this stuff is, marking S is visited, this is like theta 1. I don't know, this is like theta V to like, set the D value for all the vertices. Creating the priority queue, it turns out any reasonable implementation of a priority queue, and you could think about all these things that we put over here, you can do all of these in theta V. If you basically start with a bunch of values and you know their keys, there's better ways to do it than just calling insert repeatedly. You can sort of create a priority queue all at once at theta V time. But it doesn't really matter because it's going to be dominated by the while loop anyway. So how many times do we do this line of code here, the remove min call? Yeah, we do it once for each vertex, right? So now, I haven't exactly said which priority queue implementation we're going to choose. So we're just going to say that this line takes I don't have too much space here. It takes theta of v times, we'll say t rem of v. Right, so by t remove, I just mean the time for the remove operation, which is a function of how many vertices are in the priority queue, right? So we can, later we can substitute this with, whichever of these things in this chart that we wish to choose. We can stick in that here and, see what we get. But in any case, we're calling that once for each vertex, so it's going to be v times however long that takes. Marking is visited is constant time. We've got like some nested loops here, but we're going to again do that trick where we say, forget about the fact that they're nested. It's just like this here, right? So for each vertex, we look at all the edges going out of it, which means that overall, in the entire algorithm, we're going to look at every edge once. Right? At some point, we're going to look at each vertex and then look at all the edges coming out of it. So all the stuff in here, like this if, is going to run e times, once for each edge, total. Right? So, checking this condition, setting this, setting these dictionary values, those are all just constant time. So it's like, theta e plus, we do this update key operation. Right, and so we're going to do this update key operation possibly once for every edge. Now, we might not do it that many times because this if may not be true every time. But it's not too hard to make up, kind of worst case graphs where you actually do this if is true every single time. And you have to do it once for every edge. So this thing is going to be theta of e times t update. Oops. Okay, so overall, it's going to take, theta of v plus theta of v times t remove plus theta of e times t update. Update. Well, and then plus another theta e, but this is definitely bigger than theta e, so we can just forget about the theta e. Actually, we can forget about the theta v too, right? Because this is bigger than theta v. With a we'll just say with a binary heap, for example, the time to remove in a binary heap, well, they're both log n, right? So this is log v, so this is theta of v log v plus theta of e times log v. And we can assume that the number of edges is at least as big as the number of vertices, because if it's smaller, then that means there's a bunch of vertices that are just degree 0, and we can just get rid of them. So this would just be theta of e log v. And we don't have time to go through, in detail, like if we choose each one of these, what does this work out to? It's a nice exercise. It's also in the PDF of the lecture notes, but, for example, if you choose a sorted list, right, then you're going to get this is going to be theta of EV. So it's going to be just as bad as the original naive version that we came up with. If you choose a dictionary, it's actually going to be something a little different. It's like theta of v squared. It doesn't really depend on the number of edges, which is interesting. I guess it's like v squared plus e. And you can work out what it is with the Fibonacci heap. I'm putting this one up because this is usually when people think of Dijkstra's algorithm, this is what they think of. And in theory, a Fibonacci heap could be slightly faster for very large graphs. But in terms of practical implementation, Usually people choose a binary heap. And so E log V, right, that is in fact better than E times V, which is what we had before. In fact, it's much better, right? So getting to replace the V with a log V is a huge win, right? I mean, think about like if V is 1,000,000, log of V is about 20. And so, you know, if you have like 1,000,000 edges and 1,000,000 vertices, 1,000,000 times 1,000,000 is way, you know, that's ridiculously slow. But 1,000,000 times 20, no big deal, right? So any last questions? All right. Have a good weekend, y'all.